All right, this is a classic deer problem. You find this in every physics. So here's your x-axis. All right, so at time 0, you're over here. All right, and you're traveling at some initial velocity. And they told us it was 60 miles per hour. You better convert that into what? So we got 26.8 meters per second is equal to 60 miles per hour. The other problem, 100 kilometers per hour is 27.777. So in Canada, where they use 100 kilometer per hour speed limit, you're going a little over 60 miles per hour. Turns out it's like 62 miles per hour, 100 kilometers per hour. All right, so we got the initial speed. We know the deer. So you've got the deer over here someplace, and we need to stop our car right before that deer. All right. So the deer standing right here at x1 is 80 meters. And here we're at our initial position is 0 meters. All right. The question is, what's our final velocity right here? 0 meters per second. Okay. And they want to know how much acceleration. The acceleration can be pointing backwards, right? Slowing down. What is our acceleration if we come to a stop right before we hit the deer? By the way, a variation on this, which is a much more interesting problem, is you're traveling 60 miles per hour, and you see the deer when it's 80 meters in front of you. But do you apply your brakes immediately? No, you have a reaction time, right? Human reaction time, I don't know, 0.7 seconds or something like that. So you'd have to account for a 0.7 second reaction time, and then you apply the brakes, and then you slow down, and it's just a slightly different problem. So you can look for variations of that problem. Okay, but this is a constant acceleration problem. Let's start our initial conditions here. We have x0 equals 0 meters, bx0 equals 26.8 meters per second, ax equals, that's what we need to find. All right. And we know that x1 is 80 meters, bx1 is 0 meters per second. All right. And so we do have, that's our assumption. So we get to use equations 5 through 10. So we need to find acceleration. What equation should we use? We could always use equation 5 and 6, because that would not only give us the acceleration, that would also give us the time it takes to stop. They don't care about the time. So if they don't care about the time, I'd sort of default to equation 8 and see if that works. Would that work for us? Do we know our final velocity? It's 0. Do we know our initial velocity?
60 miles per hour.
We don't know AX, that's our unknown. And our delta X is 80 meters. Alright. The question is, are any of these numbers negatives that I just put up here? This one's going to get squared away, so I don't really care. That one's going to be positive regardless. What's that? The acceleration we expect to be negative. Is delta X positive or negative here? What's delta X? It's X final minus X initial. Our X final is 80 meters, right? Our X initial is 0 meters, so that is positive. So when we work this out, in fact, if we actually just solve this thing for acceleration, AX equals what? Subtract the x naught to the side and divide out by the 2 delta X. And that's going to give you a negative in the end, right? Because that negative there is not going to get squared away. And that's going to give you your answer. Do that. I'm going to take my converted number, which I have in here, I'm going to square it. Divide by 160. negative 4.49 meters per second square. And that's our answer. Okay. Yeah, so there's variations on this. Like one will say, if your acceleration is such and such a rate, how much reaction time can you have so that you avoid the deer? And 2C problems. All right, so 2C had that variation of this problem. All right, do you want to skip over that one? Do that one now. Now they know how to set it up. All right, so what number is that? So 58. So see 2C number 58. That's a more interesting version of the problem. Now that we know how to do the basic setup. Okay, so this is a more interesting variation of the WebAssign 2B number 33. Was that right? Mm-hmm. So there's a more interesting variation of it. So, Ranger National Park driving at 32 miles per hour when a deer jumps into the road 225 feet ahead of the vehicle. After a reaction time T, all right, that's our unknown we're going to look for, the Ranger applies the brakes to produce an acceleration of negative 9 feet per second squared. What's the maximum reaction time allowed if she is to avoid hitting the deer? All right, so let's draw a diagram here. And so we've got our x-axis and feet. All right. And so we've actually got two phases of motion here. We've got, let me just look at this A, B, and C. All right. So from we're going to call this 0 feet here. All right. So this is when, at this point, the Ranger just spots the deer, and at that point in time, the Ranger's moving at so we'll call it dxa equals 32 miles per hour. And then they spy this deer in the distance. And how far is that deer in the distance?
225 feet.
So this is 225 feet. They spy that deer in the distance, but you've got a reaction time. This is TA. This is TG. So if we start this out at 0 seconds, we've got this reaction time that it's going to take for her to apply the brakes. And so from time A to time B, we've got no acceleration. She's just going at a constant velocity. All right. From time B to time C, she's actually applying the brakes. We have an acceleration pointing backwards, and they tell us what that is. Negative 9 feet per second squared. Okay. So over this first time frame, we'll call this phase 1. We're moving at constant velocity. And over phase 2, you're moving at a constant acceleration, slowing down. Okay. And we hope to stop right before we hit the deer. And so our velocity right here, hopefully, is going to be 0. So velocity at C is going to be 0 feet per second. I mean, and I've done this before, as I mentioned, right? You can hit a deer like 10 miles per hour. It will survive. So if we needed to, we could always bump them to that, I suppose. But this is a nice rating. They don't want to hit the deer. Plus, I have a broken grill, so we don't want to break the grill. So, all right. So that's our setup. But we've got two parts of the problem to look at. We've got this part and this part. So here we can use equations 5 through 10. On this part, whenever you have no acceleration, the equation you're going to have to use is speed equals distance over time. All right? Because it's your average speed, which this formula is to calculate an average speed, is the exact same as your instantaneous speed, so you get to use them as one and the same. So whenever you're just coasting, I would always default to this equation rather than going to our more complex equations. All right? And so the key item that we want to find is we want to find this time that it takes to the time she has to apply her brakes safely in order to stop from hitting the gear. So what do I do? What should we do? We've drawn a diagram. We've listed all of our knowns on this diagram. What do we do next? So what we do, let's just set up some equations for this portion here. All right. So we don't know what our initial position is for this. So that's a little bit of a problem. So we know that for this phase 2, our x naught equals, we don't know what it is. Our Vx naught, though, is our 32 miles per hour, which we better convert. 32 miles per hour, we have 60 miles per hour for 88 feet per second. What do you get when you do that? 46.9%. So you have 46.9 feet per second. And we know that our acceleration is negative 9 feet per second squared. Alright. Our final position is, well, we're not sure. Alright. Problem is, we've got this little bit of little bit of motion here that we've done, and let's just make up a variable for this amount that we've traveled. Let's call this we've got this delta x that we need to figure out, and we've got this delta t that we need to figure out. All right. So our x final is going to be our 225 feet, but minus our unknown delta x. We don't know what that is. All right, and that's the trick to this problem. You're traveling at a constant speed, right? So we know speed equals distance over time. Whoops. And this is the time that we need, right? And we don't know this distance. That's our delta x. So we get speed equals delta x over our. That's our missing. We need both of those things. We need to know. All right. So we have 46.9 feet per second equals. That's the distance we traveled while we were waiting for our dust to press the brakes, and the time it took us to press our brakes. And really, we want to know what that's our number we want to know. All right. So we've got two unknowns in that. Let's actually set up some equations for phase 2. Problem is, so we've got one equation with two unknowns. So as soon as I see that, we're going to end up with a system of equations we've got to solve. Okay. So we have Vx final squared equals Vx initial squared our acceleration at delta x. All right. We know our Vx final squared is 0. All right. We know our initial speed was our 46.9 minus 2. Ax we're given, right? It's negative 9. And our delta x is what? We're looking for that. This is going to equal what? Given that that's 225. So we got 225 minus delta x. All right. 225 minus delta x. All right. What do you notice about this equation? How many unknowns do we have? What one unknown? So this one we can solve for delta x. All right, we can solve that for delta x, and once we get that, what can we do? And we'll take that answer, and we'll plug it in right there, and then we can solve for delta. And there's your answer to the problem. You guys do the math. So.